All right, here we go. Now we're talking about this one. And in fourth period today, I told you I screwed this one up. So this is a really good one for you to see. What are your moments of time going to be, please? Everybody look at 3. Okay, what's moment in time, like state 1, let's call it. First moment in time, what's that going to be?
When mass is at its highest point.
Be good to get everyone involved here. So, say that again. Moment in time 1 would be what?
When mass 1 is at its highest. Yeah.
Okay, so it's now. Is it moving yet?
No.
Rest.
Okay, I'm going to make a suggestion here. This problem's hard.
No,
and mass 1 is greater than mass 2.
So if you release the system right now, would you guys agree that mass 1 is going to go down to the floor, mass 2 is going to travel upwards?
Yes.
Okay, good. At the moment of release, would you agree that the velocity is 0 at that moment?
Yes.
Okay, so that would be important. So at this moment in time, velocity is 0. And I'm going to argue for us doing system 2 and gravity field. Okay? I think you'll see why later. So I'm going to make it M2 and gravity field is my system. Are you guys good? She asked a beautiful question. Why gravity field? Need to say it louder.
Because they are in the air.
Well, yeah, is M2 going to change height?
Yeah.
So gravity field will become important there. Go ahead, David.
How do we decide on which mass to choose?
That logic will become apparent in a moment. So here's why I chose mass 2. Mass 2 is being pulled. Here's my pulley. Mass 2 is being pulled up. At some point, mass 1 will hit the ground. Now, I want the moment in time just before that, or maybe mass 2 will hit the pulley. Either way, the system's going to be at maximum speed at the moment before this one hits the ground or that one hits the pulley. At the moment just before that, would you agree that's maximum speed? So that's what I want. That's my second moment in time here. Vmax at this moment. And that would mean this guy's moving up, this guy's moving down. Their speed's actually the same. You guys good? So the reason I chose mass 2 as my system as opposed to mass 1, if you notice, which way is mass 2 being pulled? Which way is its displacement? Is the energy going in? Is the energy transferring through work going into or out of our system? I'll ask again. Is the energy transferring into or out of our system through work? Yeah, it's going into our system because the direction of the blocks being pulled is the same as the direction of its displacement, right? So we definitely have work going in. Work is a synonym for energy. It just means energy that's transferring. Cool? Okay. Now let's start talking about our storage bins. We have EG, EK, E-elastic. Now this isn't meant to be a bungee cord. We will be absolutely obvious when this is meant to store elastic energy. We don't mean that here. So don't worry about elastic energy. You will see the words bungee cord or rubber band or spring or trampoline or something interesting, okay, that is definitely elastic. So EK is what? In the beginning. So this is one we don't have to worry about. That one we don't have to worry about. Let's talk about over here. EG, EK, elastic. Okay? Nothing to worry about there. EK, we're going to have some. EG, wait a second. Hold on. Object 1 is at its lowest height. When?
Right when it hits the floor.
So this is one of those subtle things. You want to think of it like this, okay? There's a height difference. I'm going to take the bottom of the block, okay? I'm going to measure the bottom of the block about here. And then I'm going to say object 1 changes height by that much. And I'm going to call that its delta H. Are you guys with me? In the beginning, basically object 1 has been lifted somehow. Would you guys agree? And I'm going to transfer this over here, and I'm going to say this is how far, this same delta H is how far object 1 falls. But it isn't falling. I'm stupid. Why am I talking about object 1? I need to talk about object 2.
You can do object 1 still.
Well, we'll do that next. Object 2 was lifted, right? Object 2 started here. So I'll measure from the bottom. It started here, and it went up to that height. That's my delta H that I'm concerned with if M2 is my system. Are you guys cool?
Yes.
So basically, energy goes in. Object 2 starts at its lowest or highest height. Okay. What's EG in the beginning then?
0.
Can we call this EG 0?
For object 2.
Are we saying there's no force due to gravity?
No.
Are we saying there's no gravity field?
No.
But can we say, since it's the lowest height, that it's our relative lowest gravitational potential energy?
Yes.
And we can make that number 0 to simplify our calculations. It's our reference height. You guys cool? So that makes this 0. We only have to worry about work going in. Do you want to include air resistance? Do you not want to include air resistance? I don't care in this problem. Okay? So, and in a bigger category than just air resistance, there's also places you can lose energy that you never thought of. There's, is this pulley spin completely frictionlessly? Probably not, even if it's a good pulley. So there are places where E-dis is more than just air resistance, more than just friction. There are other places. What about sound? If there was a sound during this, isn't sound energy leaving your system?
Yeah.
So there are a lot of places we are ignoring this big category called E-dis in this problem. Ignoring. So the least we can do is make ourselves aware of what it is we're ignoring. We're ignoring the grand category of all energy lost by our system to small things, small molecules. Good?
Well, it's not anything that's,
No, this thing might not spin completely freely. That's a big one. You good?
Yeah.
And there are other things. There are other things, but I don't want to get all crazy. Those are the big ones in this problem. Air and the pulley. The pulley is probably a bigger factor than the air.
Yeah.
Right? Yeah. It's fun to think about these things, too. It's good for you. Hit equals, right? How many blocks, please? How many blocks going in? Make up a nice number, please. Okay, 4. You guys good? Where do these 4 blocks go, please? If we're ignoring E-dis, where do they all have to go? How about everybody? Now, I have a question for you.
Which one gets more?
Right now, do you think I care if you distribute them equally or not? Do you think I care?
No. As long as it's the same.
Because you have no equations right now. You don't actually know how much is going to end up as EG, how much is going to end up as EK. You have no way of knowing, right? You have just your intuition. Use that and make your best guess. You want them half-half? You want more to go in one compartment than another? I don't care. What do you want? Okay. 2 there? 2 there? Is our equation consistent then? And we should have 4 here, right? 4 here. Okay. So you always want to check if your equation's consistent. Equals 2 plus 2 plus 0. Are we cool here? Obviously, this equation is going to get a lot more complicated when we have an equation for every one of these terms except u dash. Make sense? You realize it's going to get a lot worse. But for now, enjoy the concept of it. Cool? Try to understand the concept, let it sink in for a day or two. Okay? And then one by one, we'll whittle at these equations. Help you figure them out with the equipment. All right. So that was with M2 as our system. Wonder what would happen if M1 was our system? Let's see how things change. Go ahead. Wouldn't
it just be well, no, elastic. Yeah, it would be just gravity.
Here's the problem. Let's make the same moments in time first. Okay? So we'll still talk about M1 at the moment before impact, or maybe I don't want that far. So
wait, so M1 is hit the ground, right?
Not yet. It's the moment before impact. You good? And do you see why? In other words, a nice way to think of it is it's the moment of maximum speed. Are you good there? Now, I don't know if M2 hit the pulley or M1 hit the ground first. I don't care. It's just the moment of maximum speed. You guys cool?
Yeah. Oh, is there 2 opposing forces? Because you have
Well, hold on.
you have gravity pushing it down, but then you also have the other one pushing it up.
Well, what's your system?
The system is mass 1.
Okay, did it rise or did it fall?
It fell. But then there's something pulling it up as well. While also
This is essential. Are you guys hearing this? Say it again.
there's something pulling it up while it's going down, which is mass 2.
Good. Well, mass 2 isn't directly touching mass 1. What's actually pulling on mass 1?
The tension is low.
So let me ask you. When there's a force on your system, which there is in this case, and that force is opposite, see how the tension is up and this thing's displacement is down? It moves down, but it's being pulled up. What do you think? Is the work going in or out of your system? Because it's moving the opposite direction as it is being pulled, right? So we're going to have work leaving, energy leaving through a force. Everybody good? It's just like stopping a baseball with a glove. Cool? Now, so I'm gonna just remind myself that that's the system I'm talking about, and I'm gonna say my system falls this far, and I'm gonna say that this is a moment of maximum velocity. Sorry, maximum speed is what I really mean. So I'm gonna use v without an arrow for speed, and I'm gonna say v is maximum here at that moment. And the height, you'll notice, the height of system 1 is minimum, right? So that's telling me my EG is going to be 0, right? Plus EK plus E elastic, which I never have worried about in this problem. And then over here I got EG plus EK plus E elastic, right? Is it moving yet here?
No.
Okay, so this is 0. This is 0. So what's the story then? Are we going to ignore EDIS with this one too?
No.
You can if you want. I don't care. It might be easier.
Okay.
It doesn't matter. You can incorporate EDIS or not. If you ignore it, you must write, I'm ignoring EDIS. Ignoring. Please don't write ignoring friction, because when you ignore EDIS, you're ignoring a heck of a lot more than just friction. Okay? Energy dissipated is a big category. So, how do I make it work? God, get it? Work. Yeah?
What else is in this?
I could go on and on. EDIS can be a lot of things. Any energy leaving your system could be EDIS, really, into energy dissipating into molecules. But if energy is leaving your system through a force, usually it's work. You could probably think of it either way. There are some approximations we could do. The reason I don't want to go on it yet is because thermodynamics is basically studying energy stored in molecules, energy and heat, right? And we'll do that. So we'll save a discussion of EDIS later. For now, it'll be a broad category of energy leaving your system to small molecules. Is that good? How can we make this equation work out, though? Ideas.
Wait, if work is going, if work is going out of the system, isn't that the same as EDIS?
In some cases, we use the equation for work to approximate EDIS. Right now, we'll call work when there's a force that's either causing energy to go in or out of a system. And we're using EDIS to say that energy leaves your system to small molecules. John, what were you going to say?
I was going to ask, are we solving this with mass 1 now, or is this like just figuring out what the forces are for, or the energy is for mass 1?
Well, now that our system's mass 1, how does this one work out? It's different than if our system were mass 2, right?
Oh, because I was going to say, because if we look at the two of them together, then wouldn't the kinetic energy be the same?
Ooh! I wish that all could hear such a cool idea. Did you miss it?
Wait, that's true.
Say it again, please.
Like if we view the two, because we did on mass 2 first, and so if we look at the two of them at the same time, then the kinetic energy should be the same for both of the M scenarios.
So you're thinking it would be a really good idea to have mass 1, mass 2, and gravity field as your system.
Yes,
And try it that way.
You can have them separately and just like side by side.
Okay.
So you could.
Could this problem be solved? Can this problem be solved using M1, M2, and gravity field as your system?
Yeah, I suppose.
I guess.
That would probably be a really good thing to do. Probably help you understand stuff.
Yeah, that's right.
But well, we gotta finish this one. We're not done with this one now. How do you finish this one? Yeah?
If we're solving for the work,
Try to speak up.
are we solving for the work that's leaving mass 1?
Right now, we just gotta make up. In the beginning is their EG.
Yes.
Yeah.
So, well, how many do you want? You can choose. Okay.
He likes great.
4 is nice because it's easy to draw. See, I draw a box with a cross. Now I'm done. Ah. Now what? Okay. And David, what do you? So how many are we losing then? Okay, you want to lose 2. David, go ahead.
Well, if John said that the kinetic energy is the same for both masses, then couldn't we also use that situation that we created for mass 2 and mass 1 at the end of the because we look at the same state?
My brain sort of blew up. Would you mind repeating it? It's normal.
Because it said that the kinetic energy is the same, well then can't we look at what we already created for mass 2 in the previous energy flow diagram and just transfer that to mass 1?
That's interesting.
Wait, so
It makes a lot of sense.
Okay, let's finish this up and then we'll try to draw it out. Yeah?
Okay, so since the work is leaving the system and then it's entering the system of mass 2, right?
Well, right now, just to finish this one up, how many of these 4 blocks are going to make it to EK? How about everybody?
2.
So you all got that, right? And let's check that our equation works out so that we got this figured out for mass 1. Then we can try to combine them. 4 minus 2 should give me 2. I think we're cool here. Are you guys good? Now, people have been saying maybe we could just have M1, M2 in the gravity field as our system, right? Now, you notice this solution was different than the previous solution. So changing your system changes your solution, right? And it just depends on what you're looking for. Cool? If I make everything my system, right? What was this, 1 or 2?
It's about the rest of it. I can't tell.
Okay, sorry. This one was like down here, right?
Okay.
Okay, there's my pulley. And then over here, I got this one lower, right? And this one's up higher. Does that make sense? Now the idea is, okay, now I forgot. Is this 1 and 2? Is it that way? Okay, 1, 2, and this is 1, 2. So we got M1, M2, and our gravity field. How do we do this? I'm going to write my energy bins first because I'm not sure what to do. EG plus EK plus E elastic. E elastic I don't have to worry about. EK is 0 in the beginning because nothing's moving. At this moment, EK should be max, right? Because velocity is max. And it's the same for both objects. Our system's basically moving. Okay? Now, this is very interesting. So, EG, EK, plus E elastic. I'm not worried about E elastic. So, how do we think of both systems here? Any ideas? Me too. It's weird thinking about it as both systems combined. But essentially,
Because if they're combined, then you have to like add the
And if they're similar to like EG1, EG2.
yeah.
well, just lump it all together.
So would you add them like the EG
Oh,
of mass 1
The energy
to
transfers
the
from
EG of
one
mass
object to the next object, right? So it's converting from, like, let's say,
You guys should listen to the homie.
it's going from, if that one's using gravity, then it'll go into kinetic. Is that what you're trying to say?
Okay, so please be specific what you mean.
I don't know how to explain it.
The energy stored where? And then Melinda will probably say something cool.
Okay, that's interesting.
Go ahead, Melinda.
Does that mean nothing happens?
Well,
Because, okay, if you're lumping it all together, if mass 1 is going down and mass 2 is going up, then, and you add the difference, then it becomes 0, doesn't it? Or am I wrong?
well,
You see what I'm saying?
yeah, it's kind of tricky, but I have a hunch if you should definitely think about it and try it. It's way harder than any of the problems on your worksheet. You can always, instead of, what you'll see is our choice of system going to be important here?
Yes.
Is it going to make problems easier or harder?
A lot.
Yeah.
I'm having a brain fart looking at this, and I'm going to have to think about it.
Yeah.
Yeah.
Because, like, one object, you know how one object gets its energy from gravity, right?
Yeah.
They'll just convert that energy into the next diagram, where they're both even. So the second one would be, they'll both be even.
Well, here's an idea. Yeah, I think I can use what the man is saying here. Which one has more mass?
One.
So, which object has more energy stored in its gravity field?
One. So,
Okay.
gravity.
So this energy that from falling,
Yeah.
this change in EG from object 1 falling is not the same as the energy
From kinetic.
2
As an
changes in EG.
Yeah.
The change in object 2's EG is a different number than the change in object 1's EG. Object 1's EG is bigger, right? Essentially, you could simplify this and say, look, if I take that mass minus that mass and I drop the object, that's how much EK I should have at the end.
Yeah.
You get what I'm saying?
Yeah, I get
But I'm not sure how the flow diagram is going to work. Hold on just 10 seconds, please. What's your homework tonight? What worksheets? Plural. Skate lab?
Where's energy storage?
Okay, I'll show you right now, and then I'll let you go. So let me go to your website real quick. Here they are. You'll want this one, and you'll want this one, and you'll need to play with the simulation to do that one. Do this by yourself if you don't want to learn anything.